Well, my name is Hans Moritz Guenther. I'm going to tell you about how stars are born and how we know that. I'm an astronomer. I don't know who of you is. And so I want to not just say, I don't want to just say what the result is. I want to show you how we get there. And that means that some of the things I show you are not going to look nice. And that's because in practice, research data doesn't usually look like this. Sometimes it does, and that's fantastic, but often it doesn't. So I'm going to tell you, as I said, what stars form. I'll tell you how you know that, and I'll tell you a little bit about how we actually work, like the social part of being an astronomer. How does science come together? Like, how do we get that data? Those types of things. Because I find that that's often what people like to know, and I think it's really interesting, and it's important of how it goes together. But when you read, the New York Times about some great new discovery, it's not going to be in there. The pretty picture is going to be in there. The discovery will be described there, but how people actually got there is usually not in there. So I want to tell you that. So how do stars form? This is the Orion Nebula cloud, an optical picture of the Orion Nebula cloud, zoomed in a lot, obviously. And then for some of these pieces, like this tiny dot here, and this, if I find my mouse, this tiny dot over there, zoomed in even more. And I'm going to talk about all these elements in the little pieces. I just want to tell you that star-forming regions are one of the things that look fantastic. Now, to orient you a little bit about what I'm going to talk about, here's a cartoon of the phases of star formation. Stars form, I showed you the picture of the Orion Nebula cloud, in these huge clouds of gas and dust. And these huge clouds of gas and dust exist in our Milky Way today. Specifically, if you travel to the southern hemisphere and you look at the Milky Way at night, there's these black patches in the sky. And that's not because there's no stars. Actually, you see that on that image on the wall over there too. That's not because there's no stars. It's because there's clouds of cold gas and dust in front of us that cover up some of those stars. And when I say cold gas and dust, I mean about 20 to 100 Kelvin, so that'll be like minus 200 Fahrenheit. And when I say dust, it's like if you lick your finger and go like this over the furniture that hasn't been cleared, that's actually pretty similar. Or do it outside. Often on this dust, there's water ice on it. So if you go outside right now and you just grab a snowball and fizzle it up, that's actually pretty similar to what these clouds of gas and dust in the universe are. And then, because these clouds all depend on little pieces, right? It's gas, particles, and dust clumps, and gravity contracts. Gravity, like all these little pieces, pull on each other so they contract towards the middle. Now, they don't always go like to the same clump, but they could go to multiple clumps. And so you form within a cloud, you form these smaller clump pieces, and these clump pieces start contracting. And as they start contracting, they get like what we call an inner core. And then what happens is when you compress something, it gets hot. If you go and fill up your bicycle with a hand pump, and after your tire is full, you touch like the valve or you touch the front of the pump, it's going to be hot. And that's because every time you compress the air, it heats up. And so the same thing happens here. And eventually it gets denser and denser and denser, and eventually it's going to get hot enough that it starts shining and we can see it. So that'll be like this inner bit here, or this inner star here. Now these gas clouds, the clouds of gas and dust, they're never stationary. There's always flows. There's like ebbs and not tides, but there's like flow over here and flow over there, and there's a big, massive, heavy star there that pulls material up. And so when you compress it from 200,000 astronomical units to just one astronomical unit, the same thing happens as if somebody on the ice like pulls their arms in, or if you want to speak physics, angular momentum is conserved. And so like a tiny motion over here gets a really fast spinning motion in the middle. And because we have this really fast spinning motion, around these central objects, you form a disk. And these disks are the reason why the planets in our solar system all orbit around the sun in the same way, in the same plane, because they're all formed in this disk. If it was random, you could have one planet go this way, and one planet go this way, and one planet go that way. But that's not what we see, because they're all formed in this disk that all rotate pretty flat around the sun. There's a little bit up and down because it's not exactly flat, but they're essentially all orbit in the same plane. And so these are the disks where planets form, and that's part of why it's interesting, because we want to look at how planets form. There's also outflows, as I'll show you, And then we'll get these rings and gaps here, and eventually we'll end up, after maybe 50 million years or so, we end up with a system with a star in the middle and a couple of planets around. And so the phase I work on is like this phase from here, over here, to maybe here. I'm looking at how this disk and the stars interact. Why do we care? Now, maybe you think that's cool, and I think that's cool, and I think it's interesting. But specifically, when I write a funding proposal and say, dear NASA, please give me $200,000 so I can keep working on that, I need to have a slightly better explanation than it's cool. Right? So one of the things we care for is the origin of planetary systems. How do planetary systems form at all? How do you make planets? And in order to understand that, we need to know what the conditions are. Is it hot? Is it cold? Is it dense? Is there iron? Is there hydrogen? What actually is the stuff made of? We can also interpret that as going back in time, because we can't see today how our Earth was formed, because that was 5 billion years ago. But we can take a telescope and look at stellar systems where Earth-like planets are forming today. And so that looking at those systems helps us understand what the conditions were when the Earth was formed and how potentially life on Earth started and things like that. And one interesting tidbit or aspect is that we think, or one idea is that life, or at least certain biomolecules, may have formed in space first and then come onto the Earth frozen in as comets. Not necessarily like don't think of an animal walking, but think of amino acids. And we know that in these large clouds of gas and dust, using radio observations, we can identify fairly complex molecules. Like originally, people found carbon, then they found carbon monoxide, then they found carbon dioxide. But we found benzyl rings, so 6 carbon atoms in a ring with stuff around it. We found molecules that have 3 benzyl rings on it. So I don't know, I don't work on radio, I don't know what the latest one is, but the complexity of chemistry in these clouds is astonishing. And so almost certainly some of that rained down on the Earth. Is that important to start life on a planet? I don't know. But it's certainly interesting that it's there and that the building blocks don't actually, or some of the building blocks don't necessarily have to form on a planet because they're out there in space and they're just rained down. And so again, for that, to understand if that's important, or if that's cool, if that's useful, we want to know a little bit more about the conditions of how stars and planets form. So how do we do that? Well, we go and look. And when we go and look, we have a choice in how we look. We have the entire, what we call electromagnetic spectrum. The thing that's most used to us is visible light, right? That's what we detect with our eyes. But there's a whole range out there. And the visible light is just this tiny bit of area of the spectrum. It's just this tiny thing here. There's UV light, there's X-ray light, there's gamma ray light, there's a huge range of infrared light, there's microwaves, there's radio waves, already said, and radio we can identify these molecules. And by building the right telescopes and the right instruments, we can get a lot more information than if we were just looking in visible light. Here's an on-Earth demonstration of why that might be interesting. These are 2 animals, right? Meerkats and freshwater crocodiles, observed in 2 different wavelengths. The top one is visible, how you would see it with your eye, and the bottom one is an infrared camera. And you see that although they look fairly similar and have a fairly similar color in visible light, they look vastly different in the infrared. Now, I'm not a biologist, but if you look close enough, that tells you something about the temperature of the animal and the skin conditions and what the skin is made of and stuff like that, if you look close enough. And so we want to use the analogy, we want to use the same thing in space by looking at more different wavelengths to probe more different properties of these things. Slight wrinkle. Many of these wavelengths don't make it to Earth. That's good because, for example, X-rays, if you have too many X-rays, you're going to get cancer, right? If you get X-rays too much. So fortunately, the Earth's atmosphere blocks most of the X-rays that come from space. Unfortunately for us, that means if we want to see the X-rays that come from space, we have to build a satellite and fly it above the Earth's atmosphere. That means it's expensive. The Chandra satellite that I often work with, or that I work for, costs about $1 to $2 billion, depending on how exactly you count it. And if something's broken, it's gone. It's in space. You can't just fly up and fix it. For the Hubble Space Telescope, where they went up with space shuttles to fix things, every time you go up and fix something, it's $1 billion. So it's not like, you can't just go and tighten the screw if you need to. So if we can observe it from Earth, that's great, but certain things we just can't because there's air in between. And so, not incidentally, the wavelengths that make it to Earth best is the visible light, which is why our eyes see visible light, because we have plenty of that there. But if you want to observe in several of these other wavebands, we have to observe satellites. Use satellites. So in X-rays, we can use, for example, Chandra. There's a second one, a European one, called XMM Newton. In the UV, the Hubble Space Telescope is still the best one. And this is a picture of the James Webb Telescope that observes in the infrared, recently seen. So there's solar panels that power Chandra. The X-rays go in here. Chandra doesn't make X-rays. It's not an X-ray machine. It's a telescope, observes X-rays that come from space anyway. Like the sun makes X-rays, black holes make X-rays, and we just need to see them. And so it's very long. Chandra was launched with the space shuttle. It's actually the heaviest thing the space shuttle has ever launched. And the detectors are here in the back. And I can say a little bit more about how Chandra is made from, or how it was made later if we get to it. Okay, I said we want to observe in different wavelengths because they give us different information. This is a star-forming region. That's what people call the pillars of creation in the Eagle Nebula, observed in different wavelengths. On the left is visible light observed with Hubble. This is near-infrared light. And then on the far side is this mid-infrared light, so even longer wavelengths. And you see that although it's the exact same region, you see different things. For example, when you look in the optical with Hubble, you see these dense clouds of gas and dust where I told you stars form. I told you stars form, but you don't actually see that because it's all hidden behind that cloud. When you look in the mid-infrared, that dust is transparent. And because it's transparent, or mostly transparent, you can see all these stars here, and you can actually go up and count them. And if you go into the mid-infrared, then that dust isn't black, it's actually glowing. And because it's glowing, we can now measure the properties of the dust. We can look at the light that comes from the dust, we can see how much it glows or what color it has, and that tells us what temperature it has, for example, and that's how we know how cold it is. I said it's about 100 Kelvin or so. That's how we know. And that's how we know what it's made of. Yes?
How do you know that a star is in the cloud and not behind it?
That's a very good question. There's several things we can do. The easiest is there's complex answer, and not every technique will work for every one of those stars. One of the best things or easiest things to measure distances is you look at it from here, and then you wait 6 months until the Earth is on the other side of the sun, and measure it from here, and there'll be a difference in angle. It's called parallax. And that difference in angle, you can use a sine and in elementary geometry and transform that to a distance. So that's one way, for example. In this particular case, that's not terribly useful because it's not that precise and the nebula isn't that deep. But if you can identify the same star in, for example, in this image and in this image, then you can say, for example, this one, you could say, there's lots of stuff behind it, lots of nebula. I can't see anything else behind it, so it's clearly in front of like this dense region. And yet I can't see it here, so there must also be still some material in front of it, so it's probably in the middle. That doesn't give me exactly what it is, and it doesn't give me a 3D map, but it tells me it's not far, at least it's not very far behind it, it's not very far in front of it, it's associated with that cloud. In other clusters that are closer by, what you can also do is you can look at how stars move, because the galaxy rotates, stuff moves around, and so when you have one of these clouds and it moves, then all the objects in it should move the same way on the sky. And things that are far away on the other end of the galaxies aren't going to move in the same direction. We call that proper motion. Now, of course, stars don't move terribly fast. I mean, if you look out at night, if you see something move, it's not a star. They move like a typical speed would be, so we take a degree, right? 1 degree of distance, which 1 degree is about this much. A degree consists of 60 arc minutes. Each arc minute consists of 60 arc seconds. And now I can't do that with my fingers because I can't make it that small. And then we need it smaller than that. So every arc second, we take it down in like 1,000 milli-arc seconds. And these stars may move, a tenth of a milli-arc second a year or so. So you do need some big telescopes and fairly precise measurements. But if you can make that, and there's satellites that are purpose-built for just that purpose, and you see that all the stuff moves together, then they're probably part of the same association. I'll talk a lot about the Orion Nebula Cloud. I already told you some of the things of the Orion Nebula Cloud, so I at least want to tell you that it is. Right? Orion is probably one of the few things most people can see on the sky, and even in Boston you can find Orion because it's one of the few that are bright enough that you can see that. I know about 6 constellations because I find that most people I talk to know 3. So if you know 6, that makes you an expert, and that's good enough. I don't have to remember any more of that. But Orion has this like popular belt of 3 stars next to it, and then you have like the feet and the hands. And just down here is Orion's Thought, and in the middle of Orion's Thought is this Orion Nebula that I talked before. So the Orion Nebula is actually bright enough that you can see it with your bare eye if you are, let's say, in Maine or Vermont or in the Mojave Desert or somewhere that's actually dark. Don't try in Boston, pointless. But in dark spaces, you can see it. Okay, so I already showed you a couple of images, and one of the techniques we learn about young stars is we do images of them. So here's real images from the Orion Nebula Cloud. I told you that stars have disks around them. How do we know that? Well, here's an image that looks a little bit like a black saucer or cigar. What that is the nebula behind it is glowing, and then we are looking at the edge of one of those disks. And the disk is colder and denser than the rest of the nebula, so it makes a black shadow. And so now we can go, and we know how far away Orion is, and we can measure the size of this, and then we can calculate the size in kilometers or whatever unit you want to use. Astronomers often use centimeters, although numbers are really high. We can calculate the size in centimeters, how long and how thick that is. Why is this nebula glowing? Why is the Orion Nebula glowing at all? It's like driving your car through fog. It doesn't glow by itself. There's bright stars that shine light on the nebula, and it reflects it to us. So it's a reflection nebula. Here's another one. And what do you see? The glowing stuff here in the middle? That's not the star. The star is tiny. The star is tinier than the tip of the mouse. But what happens is that around this disk, there's other gas and dust. The star can't shine through the disk because the disk is too thick, but it shines upward, and stuff gets reflected, and we see the reflected light. Even more obvious here, the star itself sits here in the middle, here. This is the black disk, left and right. It goes kind of diagonally that we look at from the side. And then this is all gas flowing out from the star that reflects the starlight. And so we can see now which direction it goes. We can see there's less here, which is why it's black. Nothing reflects here. There's a little more here. We can learn about how gas flows out from stars. Here's another thing. Here the star sits here. It has a disk. And what you can't see, because there's a cutout, way over here is a very bright star. This very bright star shines on that disk and evaporates it. It's so bright that it essentially boils off material and then reflects and shines. And so what you see here is a reflection from this material that boils off the disk. Why do we care? Well, if you want to know how planets form, we need to know how long these disks survive. Like, do I have 1 million years to make a planet? Do I have 100,000 years to make a planet? Do I have 10 million years to have a planet? And so one thing that matters is there a bright star nearby that boils off all the material? And so we measure the size of the disk and calculate the mass of a disk when there's a bright star nearby and when there's not a bright star nearby. And we can say, okay, bright stars are bad for making planets, at least when you're close enough. And now I'm saying bad, but of course you could imagine working out a number and saying if the star is this bright and I'm this far away, then it's going to evaporate X kilograms per second. Right? I don't have that number on top of my head. I'm not going to bore you with the exact number anyway, but you could calculate that. Yes?
In that picture up there, that center part you said is the disk, right? And
yes.
On either side of the disk, is that the young star forming or 2 other stars?
Here?
No, on either side, the bright lights.
Those are not. The star itself, there's one star forming here in the middle, but you don't see it because it's behind the disk.
Oh, it's
right?
behind the disk.
So if the disk looks like this, right, you're looking at the edge of the disk and the star's here, by the tip of my fingers. You don't see it. But there's stuff going in and out. There's gas and dust on the top and the bottom of that. And so the star shines on that dust and it reflects back to you. Imagine me taking a flashlight and putting it in the fog up here. You're going to see the fog or the nebula up and down below. even though there's no star, because the star shines in it from the bottom. The disk has a hole in the middle, and so the light can't make it through this thick layer of disk, but it can make it up. And then if something is here that reflects it, let's say a piece of ice, then it goes into your direction, you can see it.
Is the disk itself relevant to the formation of the young star?
That's what I'm working on. So yes, it is. Yes, it is. No. No need to apologize, right? Yes, it is. That's a reasonable question. That's a question you should totally write an answer proposal and find out. Now, we know some about it already, so we probably have to say a little more than let's do that. But at this stage, most of the mass is already in the star. But if you look at our Earth today, right, there's only planets left and the disk is gone. And so we can measure or calculate how massive is that disk and what mass do we have in our planets. Like just take the mass of Mars and Earth and Jupiter and Saturn and add them up. And it's only about 1% of the mass of an average disk. So where does the rest of the mass go? Well, some of it falls into the star and some of it evaporates off. And what fraction goes where? Well, that's what we try to measure, right? And that influences the star in some way. How exactly? Depends a little bit on the star. It could change, for example, the chemical composition, because these disks, as I said, are made of ice and dust. Does the gas, like helium and hydrogen, does it evaporate off first and all the metals clump together and make planets? Do all the metals then fall in the star? Do mostly the gas falls into the star? That's what we want to measure. Okay, here's a couple more images. Here's images of jets. And I already talked about proper motion, where you see things move on the sky. This is the famous star called HH30. And the star's in the middle, and you see the disk on the side again, and then you have like this jet, this really collimated stream of stuff going up and down. And here we can measure how fast it's going out from the star, because we have pictures from 1995, 1998, and 2000. And so you can take like this dot and measure how far is this dot from the star. And then you can look at the same dot 3 years later and see how far away from the star is it now, and how far away from the star is it now. And if you know how fast the way that thing is, how far away it is, then you can calculate how fast it moves. And it's around 300 miles per second. And that tells us, well, we can take the star and we can look at the gravitational energy and say, where does it come from? This jet is not formed in the disk, because disk doesn't have enough energy to make anything that fast. So this jet must be coming from very, very close to the star. And so the material that's thrown out of the jet is stuff that's from the star, or that's at least from the inner edge of the disk. It's not something further out. Now, I'm not going to give you the answer to everything, right? Because first of all, I don't know it. We also still do research on that. And there's literally hundreds of people researching that. And I can't tell you everything that hundreds of people have spent the last 50 years working on in 30 minutes, right? But that gives us information about where that material comes from. Now, this is a jet that I've looked at. And this is one of those cases where I said images don't necessarily look good. So this is observed with the Chandra X-ray telescope. And every dot, every gray dot here, every light gray dot is one photon, one piece of light. Every dark gray dot is 2 pieces of light, and every black one is 3 pieces of light. So this is, each of those images is about a day of looking at that star. You don't see the star itself. The star is where these little X's are. Or you barely see that's the star itself, because again, it's one of those cases where we are looking through the disk from the side, and then we are interested in the jet that comes out. I showed you that picture before, how the jet moves, how this jet moves in the optical, observed with Hubble. We would like to know if the jets that we see in X-rays also move. So first of all, we need to find one, and then we need to find a feature that moves. Look in this gray box here. In 2001, there's one piece of light. In 2005, there's 1, 2, 3, 4, 5, 6, 7 photons pieces of light. And then in 2009, there's only 2. So I think that means there's material that came from the star that wasn't there in 2005 that moved into that position in 2009. And then it cooled off. And so it moved out and cooled off, so we can't see it anymore. Now that's from 2 and 7 photons and pieces of light. So we try our best, but if you want to make a pretty picture in multiple different images, go ahead, right? It's going to be hard. But that's why Yeah, depending on what research you do and what you look at, sometimes it looks good and sometimes it doesn't. So what we find is from stuff like this, the things the jets that shine in X-rays are faster than the ones that shine in the optical. And what we think that means is that jets are not like a homogeneous stream. It's actually layers of streams, like the layers of an onion. There's something in the middle that's faster, and then there's an outer layer that's a little slower, and a layer further out that's a little slower, and a layer further out that's a little slower than that, until you get like a very slow motion out to where the disk is. And again, that tells us where the disk is coming from. Is it coming from the star? Is it coming from the disk? We can measure those things. Okay, back to the Orion Nebula Cloud. I think I've showed that picture a couple of times now in different images. I've talked about all the pieces. Here's an X-ray movie. So this is a month of looking at the Orion Nebula Cloud. You see that it's twinkling, and you see that some of them change colors. Every one of these dots is a star, and you see that they're becoming brighter and fainter. I should first say, when you look with your eye and you see stars twinkling, that doesn't mean anything. It's because the Earth's atmosphere is in the way. If you were to take your eyes into space and look straight into space, well, okay, you die because you need to breathe. But apart from that, stars wouldn't with very, very few exceptions, they wouldn't twinkle. The twinkling is the motion of gas between us in the Earth's atmosphere as wind in high layers that refract the light and break it. So it's actually very annoying when you do telescope observations on the ground. You have to try to correct that. But in X-rays, stars become brighter and fainter significantly. Like sometimes they become 20 times brighter. And so you see things appearing here that weren't even there before. We can show that in a different way. And that different way is what we call a light curve. So what we do is we have the time at the bottom, in this case in a unit called kiloseconds, right? Because that's what you do. You do meters, centimeters, and kilometers. There'll be grams and kilograms, so there'll be seconds and kiloseconds. But whatever. And so we measure how bright it is at this time where we start measuring, and then we measure how bright it's here and how bright it's here, how bright it's here, and we measure how bright it's there. And it suddenly becomes a lot brighter. And we call that a stellar flare. See this in X-rays, and sometimes you see it in the optical, although in the opticals they're not as strong. Like they're so weak you wouldn't see them with your bare eyes. How do we know what that means? Well, it'd be great if there was a star nearby where we could see what those things actually mean. Turns out there is one, and we see it every day. It's the sun. So here's a similar event on the sun. This is taken with a satellite called SDO. And you see these arc loops here. Now I've picked one where these arc loops happen to be on the side of the sun because then you can see it much better than when it's in the middle and the sun is behind. These are magnetic field lines. The sun has a magnetic field, and there's essentially like a north pole over here and a south pole over there. And then along these magnetic field lines, the gas can heat up. And when it heats up, this is a movie taken in the ultraviolet, then becomes hot enough to shine in the ultraviolet. So I play it again. And you see that depending on what the magnetic field lines do, more and more of these arcs can light up. And so you can imagine if I take the entire image together and just say how bright is that image all over without knowing where it's are, now it's brighter than when I started the movie. So we can look at the sun where we have actually a lot of detail how these flares go. And then say, okay, it's probably happening very similar on other stars, except other stars are brighter and the magnetic fields are stronger and like we can compare that. Here's another one. So we call a coronal mass ejection, is stuff flying out of the sun, matter flying out of the sun. Now you might imagine if that hits a planet, that might do something to the planet. Right? And so
Disrupt their iPhone network.
in fact, it does. These particles, coronal mass ejections, when they hit the Earth has a magnetic field, and the magnetic field of the Earth shields us from most of that. But the really strong of those effects, the really strong of those things, they can knock out satellites. They disrupt satellite communication. If they were even stronger, the strongest one that Earth has experienced, called the Carrington event, after a guy named Carrington who wrote a lot about it. That was in the late 1800s, shortly after the US had the first telegraphy lines. And the magnetic field wobbled so much that the telegraphy lines started giving sparks in all directions. and people got hurt like from standing close to the machines. Now, if you imagine doing that to the internet today, like where we are far more connected and have far more data lines and have like electric wires everywhere, it's not clear what that will do to us. We just hope it doesn't happen. That's an important part. But so understanding stellar activity, how likely these events are, how big they are, how can we prevent them, does have practical applications to us too. Okay, another thing we can do is we can do spectra. We can look at spectra, another tool. And so spectra is just the color. This is the spectrum of the sun. If you look at the sun close enough and then you put it through a prism or through like split it out in a rainbow, or 10 years ago I would tell people to take a CD and sprinkle rainbows everywhere. If you look close enough, you're going to find these black lines in there. They're called Fraunhofer lines after a guy named Fraunhofer who discovered them first. And it turns out each of those lines is specific to a specific element. So this one, for example, is sodium in the orange here. And that has something to do with how an atom has a nucleus and has electrons around it, and the electrons go like one level up or one level down, and there's a specific change in energy, and every specific change in energy is a specific color of light. Fortunately, we can do the same experiment at home or in the lab, and we can measure which element goes with which color, and then we can say, oh, this star has a very strong line, a very strong dip or rise where we expect sodium, so this star must have a lot of sodium. You can in fact do some of those experiments at home. If you have a gas stove, the flame is blue, and if you take some sodium chloride or salt, if you take some salt and dribble it in, the flame will become orange. It's a great experiment for kids. Great, an adult has to do it, right? Because you have to get pretty close to the flame. But that's the closest you'll see atomic physics, like in your kitchen. And so we do that for a bunch of elements and compare that to what we measure in the lab, and then it can tell us what elements are stars made of. And so we know the sun has mostly hydrogen and has some sodium and has iron and has lithium and has all sorts of things. And we can measure how much does this star have, how much does that star have, does it change with the age of the star, does it change with the star having planets or not having planets. We can compare those things. This is a spectrum, how it looks in the X-rays, and there's other elements, and I just want to show you that that's how they look. I don't want to go through every new line and tell you what they do. I just want to show you some data that I have personally worked on so you get an idea of how it looks. That means most of my work looks like this. Now, astronomers do not wear lab coats and we don't work all at night. Very, very rarely people actually use telescopes. I mostly use space telescopes, so I don't ever get to look through them. I don't ever get to go anywhere. People I work with, some of them use ground-based telescopes, like in Chile, for example. And fortunately, we don't have to fly to Chile for that anymore. Like people used to fly to Hawaii to use the telescopes in Hawaii. And while I would love to go to Hawaii at some point, people tell me if you go 10 times a year, it's not fun anymore. Because you fly out from here, you're 12 hours off. 12 hours jet lag, right? You have one day to get used to Hawaii, then you get to the bottom of the mountain. Then you have a day to get up the mountain. Then you need to get jet lagged by another 12 hours because now you suddenly have to work at night. Because that's when you use your telescopes, right? And then you do it all in reverse again. And so people would fly to Hawaii or to Chile for like just one night of observations. And that's not just expensive and a pain, it's also a huge carbon emission. And I'm very glad we have the internet today and don't have to do that very often anymore. Sometimes you do, like if you build your own instrument with very specific instrumentation, you need to go and screw it on the telescope, then you need to be there, right? But for many cases, many things can be done remotely. And most of the data, all the data is from space, all the data NASA has taken, you can go and download. It's all public, it's all free. I'm not sure it's useful to you because the file format might be a little bit obscure, but you can do that. And so I work in an office. I write code. Most of my time I write Python code or I write text. That's my job. Okay, specifically for space telescopes, I said, and I know I'm running 5 minutes over, but I'm almost done. So the way Hubble works or Chandra works, right, there's only one Hubble and it's not owned by any particular person. So how do we get to use it? We essentially, once a year, NASA writes proposals. So we write a letter that essentially goes like this. Dear NASA, I would like to look at IM Loop. I think IM Loop is a really cool star. Okay, a little better than that. IM Loop is a star that is younger than TW Hydra and that has signs of a disk of accretion. We've looked at TW Hydra before and we want to know if if what we've seen there, if that's true for all young stars or only for stars that are 10 million years old and if younger stars behave slightly different. Then I go that and I send it in, and some group of people is going to look at that. Because every year NASA gets people asking for about 9 years or 8 years of data. Now there's only 365 nights a year, so there's only so much you can do about it. So there's some committee that ranks them and says, this is the most likely, and this is a crap idea, and this won't work technically. And this one we like, but we just didn't have any time left. And so you send it in for Chandra, you send it in March. Then in June, you get an email back that says, sorry, we're not going to do it. And we aren't going to do it because you didn't really describe how long you need to look, or something like that. So next March, in the second year, you can update your proposal. You can send it in again and explain that better. Let's say the second time the committee accepts it. Now that goes in annual cycles, right? Your star isn't even visible all the time because sometimes it's behind the sun and stuff like that. So the stuff that gets approved in June gets observed sometime between August and the August the year after. So depending on how that falls, in this particular case, it took, even after I sent it in, it took 1 year and 2 months for me to get that data. Then I take that data and I observe it and I analyze it. Took me a couple of months to think about what it really means, and then I write it up in a journal. And now I go and say, okay, maybe we need to look at a star that's even younger, or that's an age between Iron Loop and TW Hydra, or that has a higher mass or lower mass or something like that. And then I write another proposal. Why did I tell you this? Well, A, that means the timeline is very, very long between when you have an idea of what you want to look at until you actually do. It's even hard to squeeze into a single PhD. And second, that's why most of us work on at least a dozen projects at the same time. Because after I wrote this in year 1, it's not like I twiddled my thumb between March that year and the March next year, right? I need to have other things to do. Said that already. Okay, and then we try to interpret it. In this particular case, this is IM loop. There's these flares here in the UV, and there's flares in the X-rays here that suddenly becomes a lot brighter. And so that tells us something about the magnetic field of the star. And then, what do we do with these results? Well, we tell people about it. Short moment. One of the things we do is we go to conferences, where there be hundreds or dozens of astronomers, and some of them work on radio observations, some of them work on optical observations. And so I looked at IM loop in the X-rays, you looked at IM loop in the radio, you learned something about the disk, I learned something about the star. How does it fit together? So one of the things people do is they give a talk, like I do now, although usually not as long. It's often just 10 minutes or so, because you don't have to explain all the way around, because everybody there has worked on young stars for at least 5 years. Or we make it a poster, where we just write the stuff so that you can grab your colleagues and say, hey, come over here, come look what I did. And then say, look what I did, and then we hold it next to each other. And then ultimately, we write it in a publication. We communicate a lot by email with other people, and then we write it into what we call a publication, a paper, although we call it paper, although it's not on paper. None of them is printed anymore. They stopped printing 5 years ago. It's all electronic only. You had a question or remark?
So when you get to use the telescope for some amount of time, only you can use it, and that's because the
NASA have
amount of data you get is a very small slice of the sky.
Yes, for most telescopes. The answer depends a little bit on the telescope, but usually. And so when I say use, like for the Chandra Space Telescope or Hubble, what I do is I fill a web form that says, look at this star with this camera for that long. And then I don't actually have to know where that star is in the sky. I can't tell you where IM loop is. It's in Lupus. I don't know where Lupus is. It's probably in the southern hemisphere somewhere. I think it is. I hope it is. But somebody else takes care of that, because it's not like any random person can use a joystick and move Hubble around, right? With ground-based telescope, that's a little different. Specifically, if you go, you are a little closer to the controls, and you can actually press a button and make the thing rotate. Okay, so just before the end, what can you do, right? If you care for astronomy? Well, one important thing is to be excited, to like it, to listen to me and other people and find out what it's about. You can observe the sky yourself. We greatly appreciate if the sky stays dark, because it's much easier to see when it's dark outside than when it's light. So for example, around in Arizona, there's an observatory in Kitt Peak that used to be a fantastically dark sky, but suburban developments, and in particular big box shopping malls, are coming closer and closer and closer, and for some reason all those parking lots need to be lit 24/7. And most of them are lit with lights that don't just shine down, that also shine up. That's a problem. More recently, Starlink. If you want to launch 20,000 satellites in the sky, they're going to whiz through our pictures. They already do. I mean, on X-rays, we are fine because they don't emit X-rays, and also our X-ray satellites are even further out. But with optical telescope, you constantly have images where there's just streaks of right through because there's all these satellites going through. Pay taxes, right? Because that's what pays our salary. That's what they said, satellites are expensive. And there's amateur astronomers who we sometimes work with. This is one as RW Rajas, a star. And this is, again, a light curve in different bands, which is why the different colors and different filters. And so those are people who just are interested in astronomy. They observe this star, some of them every night, some of them only every now and then they upload how bright it was when they looked at it in that database. And even years later, I can go and say, now I have something interesting about how the RWRJ. I wonder what it did in the last couple of years before. And I pull this data and say, oh, this isn't actually the first time it suddenly became dimmer. It already went very dim over here. I wonder what that means. Right? But if nobody looks, I wouldn't have known. There's also things where you can go through other astronomical data and help look at classified, like on an iPhone app, and say, this looks like 2 stars. There's one over here and one over here. Whereas in other pictures, there's only 1. And why does it matter? Well, with a good camera, we can see it's 2. Pen stars is a good resolution. If you look at it with an infrared telescope, where everything is a little more washed out, these 2 stars might shine together. And so you see it's bright, but it's actually bright because it's 2 stars. It's not because the one is bright. And so there's programs like that where you can do observations or look at observations if you want. Okay, stars form in large molecular clouds. Young stars are surrounded by disks. In this disk, we form planets. Or the stars form planets. We don't, but we observe planet formation. Young stars have these powerful outflows, these jets that drive stuff into space. Star formation happens right now in the Milky Way. It's not over. Even though Earth is old, stars and planets are still forming almost everywhere. And we do many different observations. We use different telescopes, so we can look at different wavelengths. We can look at different aspects to better understand how that works.
And are you able to see stars forming in other galaxies as well?
Yes. I don't, because I specialize in stars in our galaxy. And that in other galaxies, they're just so far away that it's hard to see. So in other galaxies, you only see the brightest and most massive stars. Things like our sun, you wouldn't see in a different galaxy. But things that are 100 times as massive as the sun, you would. So things like our sun, you don't see individually, but if there's many of them, you see them all mushed together, right? So we know that happens. We know that stars form in other galaxies. We have these mushed together images. I personally study things where I can look at individual stars and get, instead of many thousands of stars, and do a sample and do a statistic over them, I look at individual stars that you can look at in great detail. So I don't, but in principle we do. Yeah.
This is a little far afield. Do you know anything about that? There's a graduate student, I think, in New Orleans. I saw this a news story on BBC, who discovered this cluster of galaxies in a structure of a ring. And she said that it's significant because it threatens the belief that's at the basis for the standard model of particle physics that with the uniform.
I read that too.
Did you hear about this?
I read that too, but I don't know any more about it than what was in the newspaper article.
Okay, I was just curious.
Yeah, I can say a couple more things. I have a couple of thoughts on that, but let me go if there's anything that's related to this talk first, and then if nobody else has any questions, I can say a few things. But no, okay. Then thanks for coming. You're welcome to stay and talk with me as long as you want. But you also don't have to feel obliged to sit in your desk just because I'm in your chair, just because I'm talking, because I know I've already run over. So feel free to run off.
Yes, yes, you like
So the basic idea is that in the early universe, right, we have the Big Bang, and so stuff starts expanding. But if you had a structure, let's say a ring or a disk, or not a disk like this, but like some material of thousands of galaxies, something over here and over here, if they look the same, or if they're connected, how do they actually talk to each other? Because a million years after the Big Bang, light can only make it a distance of 1 million light years. So if let's say this today, like in my star-forming regions, right? Stuff, if there's a bright star, it shines on this star, it illuminates it, this star evaporates, and that all makes sense. But if this star can't see this one, because the universe isn't old enough for the light to go from here to there, how would this star know anything about this one?
Could there just be something in the structure of space-time itself that organizes
how
things?
we think, or the current idea is that information, nothing can travel faster than the speed of light. Gravitational waves don't travel faster than the speed of light. The structure of space-time doesn't travel faster than the speed of light. So any structure that's bigger than the age of the universe times the speed of light at the time when it was formed shouldn't be there.
Oh, you're arguing that.
That's the basic idea or the basic problem, right? And so the headline I read from that article, I think I read on the New York Times instead of BBC, so the text is slightly different, right? But it's based on the same press release that's from the AAS conference last week in New Orleans. The basic idea is that they argue that the structure is so old that at the time, light didn't have enough time to travel from one end to the other over the age of the universe at the time. So that structure shouldn't have formed because the universe, like there was no way information could have communicated around.
So in the inflationary model of the universe, doesn't the universe expand fast?
It does, but it does so for the first like billions of a second or something like that, or millions of a second. Like, no, there wouldn't be galaxies are later. Now I don't work on early cosmology, so maybe it's in millions, maybe it's 100,000 of a second, but it's tiny. It's too early for that. Yeah, there's multiple other things that could be going on, and I don't know, and I'm sure these people have looked into that, but I don't know. One thing that has happened in the past is that people see structures where there aren't any. This ring looks very good, but if I were to just throw like chalk pieces on the chalkboard, and you didn't know how I made that, you're probably going to find some structure in there. You just need to look at the night sky. People see, the Orion there, or they see Leo, or they see, and there clearly isn't a line up there, and those stars have nothing to do with each other because we see them on the sky. That even stars that look close on the sky, one of them is over here, and the other one is like far out over there. They have nothing to do with each other. So our eye is trained to recognize patterns. Now people know that, and there are statistical tests you can try to do that. I'm sure the people who wrote this article have done that, but it's certainly a thing people will look into very carefully and say, what's the probability of that just being by chance, right? Now, the image I saw in the press in these rings looks pretty good. But I haven't seen the original images, and I'm not an expert in that field. So I said I'll give you some thoughts, but I don't have an authoritative answer, right? I mean, if you imagine going from this image to something that looks more like I'm looking for a drawing. Looks more like this. There's some processing that happened in between that we are not cheating in the sense that, for example, like why is the near infrared red and blue? Like our eyes can't see near infrared, right? So we need to assign a color to it. Like the doctor does when you do x-rays of a broken hand, they print it in black and white, or they could print it in red and blue, or whatever color they like. You just need to print it in some color scale that the eye can see. Because X-rays aren't red or blue or white. They're just X-rays, and our eye can't see them, so they don't have a color. They have X-ray color, but we can't see that. So just like an Instagram filter where everything you can turn everything that's green into blue and everything that's blue into green. You can do that, right? And so we turn everything that's X-rays into green and everything that's mid-infrared into blue or something. And so there's processing that happens to make it visible. You have to make sure that processing is right, and I'm sure the people who did the research tried that, but then when you just see the image on the BBC, it's probably the more processed version. So you would want to see how the less processed version looks like, right? I don't know. I don't know which image they used. I just say there's many steps in between, and if you want to understand the details, you have to look at all those steps. And I haven't done that, and so I'm going to stop speculating now, right? Because I don't know any more than that. But yeah,
many steps.
Yeah.
So we can't just look at an image and think that's what we would see if we were, above the dust.
I mean, we are not. We didn't draw these images. We didn't make them up, but we clearly manipulated them to make things more visible and stand out. The same way as you would, when you post something on Instagram, you put a filter that softens it or highlights the background, or reduces like that solar glare and gives you the more details in the faint parts, or that highlights the solar glare and removes all the details in the faint part. So there's steps in between depending on what you want to look at.
So there will be actually not the colors that we will see like accurately if we ever go to the space. It's not that it's going to.
It's not going to look like that. Part of that is so even the visible light, this is using this is Hubble, there's a 2.4 meter telescope. Whereas the pupil of your eye is about this big. And Hubble looked at that for about an hour or 2 hours or something like that. And so you collect all this light for a very long period of time using a really big mirror. If you look the same way with your eye, you're going to just see the light that instantly arrives in this area. And you can test that by looking at something you can see with your eye. Go out where it's dark and look at the Orion Nebula. And while I tell you that I have the Orion Nebula somewhere, while I tell you that this is the Orion Nebula, it's not going to look like that when you look with your eye. It's going to be a little fuzzy thing. Like, add another image. Now, this is a little closer, but go to the other end of the room and take your glasses off. And that's probably closer to what you would see with your naked eye. But that's like on Earth, you use a magnifying glass. That doesn't mean it's fake. It just means it's seen through a magnifying glass. Or, in your and my case, through our glasses. Right? When I see you better this way, that doesn't mean it's a fake image. It just means I see you through your glasses, whereas now I don't. And so similarly, like there's magnifying, there's longer exposures, and there's filters that think of it as polarizing glasses that take out the solar glare. That doesn't mean it's fake. It just means or sunglasses. You use sunglasses to make it a little darker so your eyes can see it better. Now, the same thing we can do with telescopes. Doesn't mean it's wrong. It just means it's seen through a filter.
And the young star you're looking at, it's as a lower left.
This has thousands of young stars.
No, the one you were looking at.
So the ones I've looked at aren't actually on this picture. The ones I've personally looked at.
Are they in the Orion Nebula?
I work on some with the Orion Nebula, but I don't know where they are. They're probably over here. So I work in X-rays, and this is like an optical image. This is an optical image.
But are they in that area?
Some of them are in that area, but the Orion Nebula is already it's not far away. But since I want to study individual stars for as much detail as I can, I look for the closest one to look at.
Is it true though that near the belt of the Orion Nebula there are a lot of young stars forming?
Yes.
That is true though, right? That is a good hot spot for young
I, in
star formation.
fact, showed you where it was.
Yeah, you showed us where it was.
Yep.
Right down there, right there.
Yep.
Orion's
In Orion's Nebula, that's where it is.
Yeah, that was it.
That's it.
That's not where that star you were looking at is. That would
I've looked at dozens of stars in different locations, including.
One that you were talking about.
The IAM loop? No. IAM lupus in lupus. If it was an Orion, it would be called something Ori.
Oh, got it. Okay.
So the stars in Orion, the brightest one is A Ori, the second brightest is B Ori, C Ori, D Ori. And then, sometimes they just get a number. If they're variable, they start with V, and then it's V12748 Ori or something like that.
Okay, thank you.
Can I ask you something related
Of course.
to what you said? Why is it important to have this connection between the stars? So you were mentioning that in the formation of the universe, so you have two stars that they might be connected or have connection. Why is that important?
And so, is it important? We try to find out what it is, right? The universe is what it is. We're not going to make a new universe. But in this particular case, and it wouldn't be stars, it'd be galaxies. Right? But the same idea. You have two objects. And if these two objects can't talk to each other because there wasn't enough time for them to exchange light or information, no information travels faster than light, we think. If there was no time to exchange information, they shouldn't be related to each other. They should have formed independently. because if they're related to each other, let's say if this star, like with stars, right? If this star evaporates that one, light needs to have time to go from this one to that one. Otherwise, it can't evaporate it. If the light can't make it because the universe isn't old enough yet. Now, these aren't going to be stars because the universe grows pretty fast, so it's going to be galaxies that talk to each other. But the same idea is if they form like a structure, like a perfect ring on the sky, then that ring must have formed, we think, at a time when there was some event that made that ring. I don't know, explosion in the middle or something that made them all form at the same time or something like that. If the structure formed that the universe was so young that nothing could have gone between here from there, why are they on this perfect ring? What made them go on that ring? Like they should be randomly located. And the probability of randomly making a ring or randomly making a triangle, whatever you want, is pretty low. So if you find structures that look as if there is some causality, some cause that made this structure, then the universe should have been old enough that that cause can actually like propagate information from, I don't know, an explosion or whatever it is, from that. Let's take an explosion as an example, right? Let's say there's an explosion in the middle and the shock wave that comes out and that forms something. Then that can only happen if when it formed, if the universe was old enough for the shock wave to actually go from the middle to the outside. Otherwise, that won't work. Like, so if there's nothing can go from the middle to the outside, how would we get like a perfect ring of galaxies?
I mean, that inflationary rate of expansion was too far in the past to have accounted for that very existence.
There's certainly things that are related to that. There's some things called baryon acoustic oscillations that have to do with this inflation. But I'm not an expert on inflation, and I'm not going to derive, the equations of the inflationary universe on a blackboard now.
Maybe Alan Booth will respond at some point.
Maybe. As I said, like this particular press release from last week, I'm sure lots of people are going to look at it.
Respond. Yeah, we'll keep our attention focused.
Okay.
Thank you.
Thanks for coming.